key just to determine what is forbidden and what is flexible and what is recommended.
Try to sort of set that out at different levels of things in this stuff.
Yes. I've seen the style guide, yeah. Yeah, we'll see you. Oh, good evening, people. We'll start with a few housekeeping kind of things. First is a new link on the left-hand side. Oh my goodness, I forgot the screens. That's what you're waiting for. Okay, on the far left-hand side, somewhere under assignments, you see mid-session exam. Okay, it's now starting to get serious. What I want to show you this evening is when you click on that, there's a button there, a link, mid-session exam, session selector. Session, terrible word. Really means to say which sitting. There will be 3 sittings, 3 periods, probably exactly the same exam, but may not be. I've got a number of exams, and I'm not sure whether I'll play with the questions or not. But in any case, there'll be 3 sittings, and there's an overlap. So people will be just coming out, and then you'll be going in, and this kind of business. So there won't be communication between one sitting and another sitting. So there are 3, starting at 3:25, I seem to remember, something like that, 3:20, and 4:20, and 5:25. If I click on that, we can see it better. They're the 3 times, and you can elect which ones. It's a bit earlier than I thought. Originally it was 4 o'clock. There's a lot of work behind the scenes to get this working. A lot of terminals, a lot of labs, a lot of invigilators, a lot of document preparation. So there'll be a small army organising all this eventually. It's just starting now, so we're quite early. So if you log on to this link, you'll be able to say which session, which sitting you prefer to attend. Okay? That's just one piece of housekeeping. With regard to the exercises, I've opened up 2 solutions and I've put out 3. Now, before I hit 3, I might just revisit the lecture from Monday, the ADT lecture, and I've made some changes there which are in some sense trivial. Let me think. What I've done is, Flavia group, eventually there will be 1 person left. If you're eliminating the 3rd person and there are 2 left, then you oscillate until you hit 3. You oscillate, you count. 1, 2, 3, boom, it goes. So you are eventually always left with 1. That's how it works. Well, what's circular in this Flavius algorithm, the Josephus algorithm, is not the queue itself. That's the curious thing. The queue, a linked list, for example, would be, what is that? Who is that? A linked list would be circular, and we'll be doing linked lists probably next week. Circular linked lists are very common. This Q is circular only in behaviour. You simulate the circularity by the statement on line 26, which is you pop an element and then you push it back on. This pop-push gives you simulated circular behaviour. It takes it off the top of the queue. You're looking at somebody. You say, OK, I'm still counting. You don't have to be eliminated. So you put them on the back of the queue so they survive. If you pop somebody and they're to be eliminated, you leave them off. You don't push them back on. So that's the basic strategy on how this queue works. Now, OK, I've popped and I've pushed here to get a certain strategy designed by Flavius. What I haven't told you, well, let's go back to our quack. This is all about a quack, which is a stack/queue. And if we go and have a look at our quack, these are all clients, black box, and now we get into our quack itself. We can see, here's our quack, quack.c, this is our implementation, this is an ADT, and okay, what's happening here? What can this ADT do? It defines at the top here a node, and it's got all of the elements in the queue or stack in an array, a fixed array. Boring, terribly crude, but okay, we're not interested in that aspect here. We're only interested in getting something working, if you like. Now, we can create a quack. We can push onto a quack. We can pop from a quack. We can make it empty, where you can see a loop happening there. Is it empty? If it's not, then you pop it. You keep popping elements until it is empty, and then you come out. So you've got rid of all the empties, all the elements, until it's empty. So it's exactly what you want. It does exactly what you want. It empties the queue or the stack. Is it empty? Well, it's just checking whether there's an element on it or not. Whether the top is not 0, it's -1. When the last one's off, it's the next one down. So it would be -1. So if it's less than 0, it is indeed empty. And finally, the only other one, function I've got on the interface, if you like, is to show me the whole quack, everything in it. Now, there's one thing missing, and that is, what's missing here? Anybody listening? Push, pop, show quack, make empty, is empty, create quack. They're the ones that I just went through very quickly. What does Josephus do? Someone? What's missing?
Missing Kush.
Yeah. Kush is missing. Where's Kush? I talked about Kush. Kush, you put it on the bottom, you pop it from the top. With a stack, it's push on the top, pop off the top. On the top, off the top. That's a stack. A queue, you pop off the stack, off the queue, but you push on the bottom, which is a kush, to differentiate from the push. So push and kush, I just work on the opposite ends of the data structure. There's no kush here. So I've lied to you. I did wonder whether somebody would pick me up. But it was such a last hectic few minutes on Monday, nobody did. So when I compile this program here, you see QUSH. QUSH is the name of a function. It doesn't exist in my ADT. It needs to be written. So I've lied to you here too, in particular. The DCC quack.c, Josephus.c, that's going to report kush, undefined. If you cut and paste, there's no kush. That's one of the exercises I want you to do, write kush. Okay, let's do a bit of thinking. I'm not sure that you're awake. Let's go back to our point. Where was our quack again? Here's our quack.h again. Here's our quack.h. There's no cush there. So the first thing you need to do is add cush prototype, which is going to look an awful lot like the push prototype. That's all it's doing. It's taking the same arguments, effectively. It's just doing something different on the data structure. So now we come in here and let's have a look at push. Because obviously, if you're going to write cush, there's a good chance it's going to look a bit like push. Okay, so what does push do? Push, well, forget the null business. If there's no thing there, that's obviously going to be the same. We're not going to not want to check whether the data structure is there, the quack. If the top is greater than or equal to height minus 1 is a check, because if it's already reached the top, the height of the, remember we had the array earlier on? I said that was a dumb thing to do, but it was the way we're doing it at the moment. Later on we could change that into an arrayless data structure if we wanted to. But here we've just got a height, an array, and we can't, of course, allow it to go outside of the array, so we've got to check that we haven't exceeded the array, that we're not full, whatever data structure it actually is. So we're checking there that the height's okay, and what do we do then? Well, the top is pointing to the top element as it is at that moment. We have to increment it, so we've got plus plus at line 31, and then we've got at line 32. At that top element, we add the input data field, the input parameter data. Can't be simpler, 31, 32. All right, that's what push does. And push works on the top. Now we want to write cush. So what will cush do? Any takers? Any thoughts? Don't want lines of C. I want a thought, a way of doing it. Contributor?
Insert elements on the bottom of the array.
Extremely good. That's a very good bottom. We've got to go to the bottom. How can we insert something to the bottom? What's at the bottom? The bottom is, well, where's the bottom of the array? What index is it? 0. Very good. You all know that. What's that 0? Probably an element. What are we going to do? Move everything forward, up. Forward, yes, forward. So we have to have a little loop to move everything up. Then we're going to have the 0 element free. What do we do then? Simple as that. It'll be something like QS arrow array 0 equals data. Now, that wasn't so hard. It's actually very simple to write. Once with push, you can write a cush in probably 5 or 10 minutes. And you need to do that if you're going to run JSFS. And in fact, I've asked you in that exercise to test your cush with JSFS. It won't work if you don't have cush done right. Okay, it's almost a trivial exercise. If you've got your thinking cap on and you know how to write a simple little loop, and you can work those QSs a little bit, sort of know what the top's doing. Doesn't require a lot of skill ability, but I can tell you now it's an important exercise. If for no other reason, I like it a lot, and I like Flavius a lot. All right, that's... now I can go back. The reason I actually got onto that was I wanted to just go through the week 3 exercise. I want to place more attention onto the exercises from now on. I'm going to try and remember to do this. It costs time, which I think, well, all this lecture time I need, but it's very important because I don't want you to ignore the exercises and just concentrate on the assignment, looking for marks in essence. But more importantly, you've got to get your hands dirty with the material. You're better off not reading my lecture notes at all, in a sense, and just trying to do the exercises and using the lecture notes then as references. Oh, I think I saw something in there, and read on demand. Don't spend all your time reading and try to understand. Spend your time programming. So look at the exercises. They will get you a lot further to the exams in the mid-session and the end. The exercises are the backbone of the course, not the lecture notes. The lecture notes are for your amusement, in a sense, are a sort of reference. If you come to this lecture, you've seen enough of the lecture notes. Immediately go to the exercises and see what you can do. Now, to be a bit more specific, those first 3 exercises, sum, I can tell you now they're only 10, 15 lines of code, and in fact, I think all 3 require just one statement. They're very simple. You scratch your head a bit, and I've got a whole lecture on that I/O business, but don't go and try to read that first. Do this first, because the questions you start asking yourself, that's what you've got to look up in my notes. You don't know what you need to know until you find out what you need to know. And that's how you learn, by hitting the problems that, my God, I don't know how to do that. I better look up and see if I can find an example. It's the way you learn how to program. So you see, I've realized I needed some text rather than see here. And this example here, for example, can you actually see what push is doing and what push is doing? And it's almost a puzzle kind of thing. So this question here is postfix stack, and the next question is postfix queue. So if you've got that expression there, 1, 2, 3 plus 4, 5 star plus 6 star plus, that will evaluate to something on a stack, if you use a stack data structure using pops and pushes. Now, it's not hard to do that. In your head, you can say, well, I know what to do there. 1 and 2, and then 3, they're all going on the stack, and then the plus takes the top 2 elements off the stack and adds them. So I got 1, the 2 and the 3 get added, and that 2 and the 3 then becomes a 5. So it's 1, 5 plus. So the plus is gone. 1, 5, then the 4 gets on, then the 5 gets on, and then there's the star. And the star takes the 4 and the 5 just before it, does the multiplication. There's 20. So I got 1, 5, 20, etc. You can see what it's doing. Now, you do that and you come up with a computation, with a calculation, and with a number in the end, assuming I've got the number of operands and operators correct. You can do the same thing with pushes instead of pushes. So when you do that computation, 1 on the queue, then 2, you push the 2. You don't push the 2. And you push the 3, and then you pop. So you're working on the other side of the data structure to pop, and then you do the calculation and you push. Okay, so now we're doing something. We're not working on the top of the stack with the pops and the pushes. That's for normal people. We're being abnormal, and we're popping from the top and calculating something, and we're pushing it to the bottom. That gives you a really good sense of what the queue is doing. from a mathematical point of view, if you like. And you really get a feel for push, what it's about. So if you do these two exercises, postfix stack and postfix queue, then I think it'll help you even more to understand, well, this push operation is not really that hard after all, and maybe there's 20 minutes worth of work there. Now this last question, matcher, you may have already done it with Python or some other language. And there are different ways of doing it. Normally, in other years and other courses, I've just said, okay, just do it, and I don't give any hints or help. But here, I think it's still early in the course, and I want you to spend your time on the C. So I've actually given you, where am I? Yeah, a basic algorithm. If you read an open bracket, etc. I've given you a basic algorithm there. That basic algorithm I wrote, actually, after I'd written the C program. If you like, re-engineered the algorithm. So I can tell you right now that don't try to be too creative, too weird and wonderful. Try to, if you like, follow my lead or follow the algorithm reasonably closely. And I think it will save you a lot of time. It is really an extremely, it's not so much interesting, it's a bit difficult in fact. In fact, it's meant to be a challenging problem for those that really want to be challenged, but you will learn an awful lot. If you do that problem, you're good. No question, you're good. Okay, you've really reached a level where is, well, you'd almost say impressive at this time of year, this time in the course. Okay, so I've given you some test cases here for you to exercise your program with. Okay, they're the exercises, and I'll put the solutions up next week. Don't look at the solutions, even if I put them up, until you've tried at least to do it. You've got to have the discipline to say, I'm not going to look at it until I have spent exactly 60 minutes on it, or 50 minutes on it, or 90 minutes on it, whatever ability level you've got. Go through the learning exercise of asking yourself or being aware of the things you don't know. If you do it the other way around and you read the answers first and try to work out what I've done, you are trying to learn my style. You won't know what you do and don't know. You have to find out what you don't know about the language. Of course, if you're really good with C, that's not that much of an issue, and you may say, okay, I'll have a look at the answer to see what Nemo has done, and is he capable? Is he a good C program or not? Okay, that's a different way of handling the exercises, and if you're that good, then it won't be a challenge for you. Okay, so that is a bit of tidying up. The exercises I've gone through for week 3, the lectures from last week, or from Monday, I call it last week. What I want to go through now is Malloc stuff. I am logging in so often every day that logs me out. I don't think that's going to be right. Yes, it is. Oh, good. All right. I would have loved to have given you this in week 1, this lecture. It's just ridiculous. Even week 2 was too hard, and this is week 3. Maybe Monday would have been nice, but we lost the lecture last week, so it is what it is. Dynamic memory allocation. Data is normally static, and when it's static, we can compile it. It's known to the compiler, and the compiler can create the data structures, the data storage, allocate everything with proper addresses in memory, and everything's fine. And for example, if we have an int, we've got 4 bytes, we've got char, we've got 8 bytes, of course it's a char star, I should say. We've got a type def here. I changed that. I fixed it up, but I didn't. Yeah, I fixed it up so that are in line the proper style. I'm going to talk about style a little bit later on as well, by the way. And I was talking to Andrew. That was, I don't know if you know Andrew Taylor, but he was the author of the style, the 1511 style. So I was talking to him about how he sees the style guide and how he works with it with his students. So here we have point P, another 8 bytes because it's a pointer, and an array of 20 bytes. Okay, in many applications you do not know how much data you will need. So for example, you have max name and max line and 2-dimensional arrays even, and you have to give them values which may not be big enough or may be far too big. So you put hash defines at the top down there and fill in some values, and you cross your fingers and hope that that's going to be okay. That can be too small and they can be too big, and both have, of course, disadvantages. If it's too small, then you're going to run into, your program will die, your segmentation fault violation. If it's too big, you're going to be very inefficient, and you'll have, and you'll never know whether it's too big, in a sense, because too big can still sometimes be too small. So what we have to do is we have to work dynamically with our memory. We have to ask for memory as we need it. And that is not trivial. We're working at a very low level here when you ask for memory from the system at runtime. The first thing you need to know, it's extremely important, and I've got a whole lecture dedicated to this, which I'm more or less skipping, for good or for bad, which is the memory segmentation for every executable file. When your program is running, there are basically 4 segments. There are the 2 fixed length segments, which is the code segment, which are all your instructions, and that'll all be converted into machine code. There's the global segment, got lots of other names, BSS segment, that fixed size as well, and that's where constant strings are often dumped. Global data is put, static data sometimes put there as well. Very compiler dependent what's put there, but what's interesting is that it's fixed length. Really, that's all that's important. You rarely touch it as such. You can write to it, your program writes to it. You don't know whether it goes there or not, of course. Your program, your compiler will decide that when it compiles the code. Most interestingly are the dynamic segments, which are the heap and stack segments, and they're defined to be working in opposite directions. So your heap has a starting address, your stack has a starting address, one moves up and the other one moves down. And it's not actually consistent. Compilers sometimes turn it upside down. But almost every compiler I've ever seen always has this upper limit, lower limit, because you've always got finite memory, and just they work in opposite direction with, and the hope is, of course, that if you need a lot of stack, you don't need much heap. So the heap room goes into the stack area, if you could call it that. They actually work together a little bit to occupy the amount of memory you have got available. So that's why that's drawn like that, with open bottom on the heap and an open top on the stack. So here we've got the heap going from the top to the bottom and the stack going from the bottom to the top. Now, there's a lot of technical detail about why things get put into the global, the heap and the stack, but in very broad terms, the functions that you call, particularly recursion, for example, where you do a lot of function calls, recursive, nothing but function calls in there. All of the function calls you make in your program, they all get put on the stack, because the stack is there to store local variables. So whenever you call the function, there's a frame that goes onto the stack, and in that so-called frame, it's just a piece of memory, it's allocated to that instance of that call, local variables will have a value. And if you call yourself recursively, then you have another instance of that function on the stack with a new value for the local variables. The same local variable with different values. So it's a bit like cloning for every instance of a recursive call. Now, if you call different functions, of course, you get all the different functions in there, and they're always nested. So you go into functions, function calls another function, and it comes out, and then goes to other. And this works like a stack of so-called frames, which are just pieces of memory allocated to every call. Okay, and when you come out of a call, that frame is thrown away, popped off the stack, revealing the next layer down, which is the caller frame. That's how the stack works for calls. The heap is memory that's available to you, and its main customer, if you could call it that, of the heap are the mallocs that you do, the requests for dynamic memory. So the stack is for function calls, the heap is for mallocs, the global data is for strings, and literally global data, and then you've got the code itself on the very left there, which is always the very low addresses. This approach is flexible, there's no wastage, only in the sense that the heap and the stack work in opposite directions. If they ever meet, of course, you've got, well, I'm not sure what it comes up with first, whether that's the heap complains, or I suppose it depends on which one is requiring memory. If you're trying to do another call, a function call, and you hit the heap, well, it's going to be out of memory. And vice versa, if you're not calling a function, but you do a malloc, and you hit the stack segment, you've run out of memory. Now, you can have variable length arrays in C, and you can, at compile time, now we're not fixing an array length, we're actually at compile time, dynamically, in execution time, dynamically setting the array length in a program. So here's an example. This only applies to 99 on. I've never done it. I've never used this facility. I don't like it very much, to be honest. It's sort of it's in between, if you like, mallocing and just having a fixed array length, which you know at compile time, a hash def. So you're in between a hash def, which you define when you're editing, and you live with it because the application will never change, kind of thing. It'll only ever need a fixed length. You're happy with it. You work with it. And that comes hash def. If you want to go past that, you need something more, I always go to malloc. But there is an in-between solution where you can have a variable length array, but that requires the user to input the length of the array, the size of something, the maximum of something. And for certain applications, that's not a bad thing. So here, I'm reading from the standard input, just scanf, no, scanf itself. I'm reading a number, and I'm calling it number of elements. And as long as one's there, I'm actually declaring a vector array, an array called vector, of size number of elements. So I've read the number in, and now I can initialize them with another scanf. Okay, so there are two scanfs going here, or actually there's multiple scanfs. One scanf does the number of elements, and the next scanf is in a loop that reads all the elements. It's quite snazzy, nice, neat. And I've just got a little example program here where I say, well, okay, I've read all the stuff in. Now I'm just going to print it all out to prove to you that it really does work. And I don't do that. Amazing. I think I've just forgotten that because with those two inputs, I should be coming out. I'm sure I did it. That's very curious. Something when an edit's gone wrong, I think, somewhere. I've lost an edit somewhere. But, okay, that's not hard to see. That compiles, and that will come out with I have read, and it will come out with from 0 to number of elements. It doesn't come out with the number of elements itself. It just comes out with the elements of the array that it's read. The program fragment generates a compile error in older versions. Yes, so you can't do it in older versions. From 99 on, it's okay. Okay, I said that's the sort of in-between solution for those where the user can type in some number and that gives you a bound on what the program needs in terms of an array size. The more sophisticated solution is to use a malloc. Now, in a malloc, we have a pointer to memory. That pointer is a byte address somewhere in memory of where something starts. That pointer gets its value by calling malloc with an argument, which is the number of bytes it wants to reserve. Now, when you do that malloc, a lot of things happen behind the scenes. It's not just simply a return address. The system remembers. That pointer is important, very important. It has particular properties to the system. It knows what that pointer is. It remembers that pointer. It doesn't treat it like all the other pointers, although you may not know that. You will only experience that when you do something that it doesn't like with it. And we'll see one or two little examples of what that can be later on. So here I have a little program called Dynamica. Love the name. It reads int from standard in into a dynamic data structure. Now, okay. Just like before, I've still got the problem, how big? This program, just like the variable program, what did I just call that beast that I just did? The one I didn't give you the input-outputs for. I called that one. Now I'm all confused. Dynamica C99. Dynamic C99 I call that. I'm forgetting my own names. And this is Dynamica, and Dynamica is similar but doesn't use arrays. It just uses a pointer. The pointer, Dynamica, gets set by a malloc on line 9. It is a pointer to a series, a set of integers. So the size I'm going to need is the number that I've read on scanf, line 7, multiplied by the size of an int, number of bytes. So I'm mallocing now, I'm reserving a piece of memory that long, number times size of int, which is 4, so 4 times number. And the starting address is Dynamica. As long as it's not null, I'm now going to read the numbers. And instead of using an account like an array, with an index into an array, I'm going to use the pointer. So the pointer is used as starting point for my index, which is now a pointer index, D. We're on line 16. So D starts at Dynamica. It goes through to Dynamica plus number, incrementing one at a time. And each time it reads its number into D, so the address in memory, so D is the thing in memory, or the place in memory that I have to put that number. That D is derived from Dynamica, which is the starting address. So D starts at Dynamica, that's element 0. There'll be element 1 and element 2, all the way up to element n minus 1. That will be the last element that gets initialized, set. So it reads it straight in to the address given by D. And I've just confirmed, yay, I've just read that number as a confirmation. I don't do anything with it. I'm just showing you how you can read data using a malloc and a pointer index. There are no, the only variable here, I was about to say no variables, there's only one variable here, int number, which has got to read from standard in how much I'm reading. We're not doing that in the assignment, are we? It's an absolute no-no. This doesn't go that far yet. The last thing I do before I come out of the if statement, after I've read the number successfully, is I free Dynamica, which I'm going to talk more about in a moment. So, if malloc returns null, the heap is most likely full. I can talk about heaps now, you sort of understand a little bit, but heap is an area of memory reserved for mallocs. There is no memory left, and you need to handle this in some way. I haven't filled that in really, except to say, well, just get out. That's often the only thing you can do at this level, because I'm not going to do error handling on top of everything else. This is a very serious error, and that's certainly got to go to standard error. I do not change the value of pointer Dynamica. It is used in line 16 to initialize my, if you like, my destination, my memory address, and then that D steps through the actual memory that I've claimed, I've been given by the system. It's very nice. Dynamica works really well. It's conceptually a lovely thing to be doing. It's not indexing an array. You can actually skip past that. That's a level of abstraction, a level of data structure. You've actually got rid of it. You can take it out of your head. You don't even have to worry about arrays and how to index them and where you are and all. All you're talking about now is addresses. Where in memory are you? And I start at Dynamica and I increment my pointer. So I'm putting the values that I'm reading from my standard input straight into memory. It's surgical. It's going straight to the heart, and to the liver, to the kidneys. There's none of this vague stuff with arrays where you're working at some high level of abstraction. An array is something that the computer doesn't really, the instruction set doesn't know anything about. Array is a man-made construction. It's artificial. You're actually putting data straight into memory. You've got your skull output, you're putting it straight in. You're trying not to draw any blood. This is quintessential C. This is pointer arithmetic. Pointer arithmetic, I'm doing here D++. That's arithmetic. D++ is D equals D plus 1. And D is a pointer. You cannot deny, you cannot say I can't see that. It is definitely pointer arithmetic. Okay? It is a beautiful piece of programming. Very simple, very C. Yes?
When D is plus plus, how many times is going to be increment D? Right? Just increase by 1.
I understand where you're coming from exactly. It's a very good question. You're thinking. That's really a good sign. The machine, if you like, or the system knows when it has a pointer what it's pointing to and will increment on the size of the thing it's pointing to. So it does have 4 bytes. And that's a bit funny to get your head around because you have to trust the machine to say, well, it's not D equals D plus 1 in the mathematical sense because that would be the next byte and we've got integers here. So they're 4 bytes. So all of you should say, yeah, but 4 bytes. Now I'm really impressed by your question because you're thinking. It does do it right. This violates the C guide, the style guide. It's okay in this course. Now, see, the problem is now, there are the document itself, the style guide, has got a number of inconsistencies and things that, what would you say? It depends on your level. A novice programmer that tries to write a program like assignment 1, not touching arrays, just using pointer arithmetic from day one, will write, 1 will probably never succeed, it'll never work, and 2, if it does work, it will probably be an excellent example of a piece of program you could send to the obfuscation contest. I asked Andrew just now what he did with his style guide, how he used it in his course, and his answer was very illuminating. He said, well, it's actually not so much for the students. It's more for the tutors and the academic. It's more or less the way we program. It's so that you understand how we're thinking and what we're trying to do. There's a huge grey area there, which is, well, it's a small grey area there which is made huge because of the huge difference in ability level. An experienced programmer will use the whole language, including break statements and continues, for example. A break statement is a beautiful statement. Used wisely, it can really be so easy to read. It's beautiful to see. It just does what it does. It stops the loop, goes to the end of the loop straight away, gets out. You know what's going on. There's no confusion. If you had to do this with logic, it can be if then else is everywhere. And it can get very confusing. You're trying to, what the hell is he doing? And why is he, what's it? And really just a break statement would have made it very clear. Break statements and continuous statements and even pointer arithmetic in the hands of beginning programmers are the tools of the devil. You will write programs that are impossible for us academics to mark. We'll look at it, we'll scratch our head, and we'll wonder what's top and what's bottom, and what on earth were you thinking at the time you were writing this, and how are you thinking? I've already seen a few programs which I just have to shake my head and think, my God, I can't do this. I can't try to understand this. I can't think, whatever this person thinks, I have no idea what it is. I don't want to spend the effort, in a sense. So, these very powerful tools, like break statements and continuous statements, and by the way, what it says about a break statement, I think it says, for example, avoid break and continuous statements. And then when you read break statements, it says, keep them to a minimum. Be very careful where you use them. So it's not even consistent in a sense. And it does say in a number of places, if you're experienced and you know what you're doing, they're fine. The bottom line is, I don't think I've ever taken marks off from any student in any of my courses because of broken a style guide rule. That's not what it's there for, really. It's not black and white. It's an intention or an indication of what you should be striving for. And above all else, it is something that helps us mark your program. If you start doing things that break the style guide significantly, like you have 8 or 9 returns in a small function, the style guide says you minimize the number of returns. And you may say, I couldn't think of less than 7. Just the function I have. Okay, so style guide allows a flexibility, but if it gives us trouble marking, then you will be marked down. It's not that you've broken the style guide in some way, necessarily. It's just that we can't read your program. You've obfuscated it. So the principle you should have, and Andrew said this a few times to me, just use your common sense. If you know what you're doing, I'll be impressed with just about anything you write. If you don't know what you're doing, stick to the really straightforward, simple. And in any case, from a design perspective, and I'll go straight now to assignment 1, start with arrays, keep it clean, work with arrays and only arrays. 2 by 2, just start with a 2 by 2 array, 4 bytes, 4 integers. Just work with that and get it working. Then worry about 3 by 3s, 4 by 4s, mallocs and all the other stuff. Get it working for something first. Get the logic right. Then start making it sophisticated. And if you need to use 1 or 2, well, I want a continued, are rarely necessary, and certainly in a simple assignment you wouldn't need them. Pointer arithmetic is a classic case. It's beautiful. I love pointer arithmetic, and as far as I'm concerned, every program should always only have a pointer arithmetic. I'm an extreme believer in pointer arithmetic in the hands of those that know what they're doing. Of course, it is almost suicide if you don't know what you're doing. You will have trouble with ampersand and star and what have I got, an address or data? What is it a pointer to a pointer? What is that? You get yourself completely knotted up and you'll find out that, you have to almost throw your program away and start all over again. And really what you should have done is get the design right, just work with an array. Because you all know arrays. These are clean, high-level constructs designed for humans to think of things, to how to manipulate data. They're very simple in a sense. And because they're also checked by the compiler, in a sense you're helped, you're supported by the compiler with array bounds. And only when that's working, then you start thinking about pointer arithmetic. And you're still careful. Every time you use pointer arithmetic, you've got to have some way of checking that you really know what you're doing, that you really do have the value you think you've got. Because in some sense, there's no protection, unlike arrays. Okay, so I show you here, Dynamica running to show you, to prove that it works. Now, Mandy. The next few slides, the next bit of wiki is about Mandy and what is data and what is pointer or what is a malloc. After all, what's getting allocated? I start with Mandy 0 and I've got a data struct some data, and I've got Mandy's age, weight and gender. Mandy happens to be a girl. We've seen this size of stuff before. We've got 2 lots of 4 bytes and a 1 byte, and it'll be rounded up to 12 bytes. So we've got a 12-byte data structure, and I define Mandy with this 12-byte data structure. And I assign Mandy an age, a weight, and a gender. And I print them out. And that's a fine little program. It's a program you should be comfortable with. It's a program you should be able to implement. It is under the level of programming I expect at the mid-session. It's certainly not enough to pass, as far as I'm concerned. Okay, this should not trouble you in any way. I have a variable, Mandy, and she's got certain data. That data is going into the struct. So it all works here. I compile it, Mandy 0, and I run it, and you see the data is being printed here, %d, 0.2f, %c, telling us that's a she. Mandy.age, Mandy.weight, Mandy.gender. I've kept it pointerless, almost deliberately. Now what I do is I say, well, can we introduce a pointer here? So I've still got the same struct, and now I've got Mandy still defined, and I've got a second variable that's going to point to Mandy. I initialize that pointer to Mandy, and I use that pointer to initialize the data. Okay, so I've got Mandy's pointer, and I update or initialize Mandy with that pointer. Started with just Mandy 0, with just Mandy. Now with the Mandy 1, which has got Mandy as a variable and a pointer to Mandy. 2 variables. I run the program again to show you it's still working. Can we get rid of the variable completely? Can I get rid of Mandy and just use the pointer? Now that should make you think a little bit, and I call this program Mandy bad for good reason. So Mandy bad, I've still got the same struct up the top, and I've got the pointer and no Mandy. Mandy's gone as variable. Just a pointer. Now you should think to yourself immediately, if I've got just a pointer, I've just got an 8-byte address. That's all a pointer is. The actual data struct, where's that? What am I going to point to? And indeed, when you try to run Mandy's age, weight and gender, as I did last time, when Mandy was there and was the destination, the place that I was pointing to, if she take it away, then Mandy pointer's got nothing to point to. So when I do that, of course, it's going to give me a segmentation violation, seg fault. Okay, because point is nothing. It's not been initialized. It's pointing to nothing, or it's pointing to some place in memory it's not allowed to touch. Who knows what's in P? But all of this is rubbish. So this is a bad program because I don't have the data reserved. I don't have room. That 12 bytes that I need, it's nowhere to be seen here. I had to have that variable, Mandy, in the first two programs to have a place to point to. Can we avoid bringing Mandy back? Well, not that I have a problem. Is nobody called Mandy here, I hope? I shouldn't. Mandy's going to get a bit of a flogging tonight, I'm afraid. I probably wouldn't admit to it now. Can we avoid bringing Mandy back? Well, yes. We can initialize the pointer with the 12 bytes that we need. So we don't give the address of the variable Mandy. We call malloc to give us 12 bytes. Then we've initialized P. So in line, whatever, 13, we see P equals the malloc. And that's given us and the size of struct some data, which is 12 bytes. So this gives us a value for the pointer. And now we can put the age, weight, and gender of Mandy in and print it out. And because I've malloc, I do a free. I'll tell you more about that in a moment. And I also do a P equals null. I clean the pointer. That should interest some of you. Wow, I've never thought about dirty pointers and clean pointers before. What would that be? What does it mean to clean the pointer? But I've cleaned them. And if you think, well, how do you clean a pointer? Well, putting null in it is probably as good as any good a way as any to do it, if you think about it. So I'm zeroing it, basically. I compile it and run it, and it works fine. This version of Mandy works fine with the malloc in it. Notice that I've just got one pointer variable in the whole program, P. P's doing a lot of work. It's getting set at 13, checked at 14, used at 18, 19, 20, printed all three ways in 21, freed in 22, and emptied in 23. So P is doing all the work. It's a pointer. That's my world. That is Mandy, in fact. But it's a pointer to Mandy, to be honest. You could ask yourself, what is Mandy here when you've only got a pointer? She has substance, but she's sort of not there too. So what is happening here really? Well, I can't think of it in real life, but when you have a variable Mandy, well, you have real Mandy. Mandy's physically there, no question. But when you have a malloc, what have you got? Have you got a spirit or a ghost of Mandy, or I'm not sure what it is. How you consider that what analogous is in real life. So, what does a function malloc do? We know, it's standard lib. Its argument is the number of bytes. If we allocate, it allocates memory on the heap. It returns the address of the start of the allocated memory. If unsuccessful, it returns null. And the heap space that is allocated to the program is actually, that program actually owns that heap space, that piece of memory. Nothing will touch it. Anything that tries to touch it will get a fault. Yes?
What's the difference between line 22 and 23?
A vast amount of difference. I'm going to get onto that. To clean a pointer is quite different than freeing it, but it's quite different. But you'll love it when you hear it. Okay, but I won't do it now because then I'll talk it twice. So, importantly, there's no variable Mandy here, and we just have one pointer, P. I could have called it M for sort of surrogate for Mandy. Now freeing. If you ask for memory and you get it, when you're finished with it, you've got to give it back. I had a program once a few years ago which I called Give It Back, which actually showed you what happened if you didn't give it back. But we get onto that a little bit later. We better watch the time today. We may actually finish a bit early today. Yeah. So I think we'll probably finish in half an hour or so, I'm hoping. So it should be freed when you no longer require it. It's a bit like opening and closing a file. That's the analogy you can think of. When you open a file, you've got to close it. Well, if you don't, as long as you're terminating the program, it's not a crime. But really, you don't want all these files open longer than they really need to be open. It's neater to close them when you're finished with something, so you don't have too many files at the same time open, because there's a sort of security problems there. You can corrupt things accidentally, because files are just pointers ultimately, and if you have the pointer wrong, you can change something in one of the files that you weren't expecting to change. The malloc is the same thing. You get a piece of memory, you free it when you're finished with it. Well, for every malloc there should be a free, a call to free. When freed, that heap space may be reused by the system. Maybe, maybe not. After freeing the pointer, still contains the address. Free just says to the system, don't touch anymore. But the value in that variable P has not changed. It's still there. And if you're not thinking, you've had 2 glasses of red wine instead of just 1, and you still try to use P further down in the program, forgetting that you were too nice and you freed it earlier on, you'll get a seg fault. The address is still in P, but the memory's gone. You've given it back. The free gives it back, but the P has still got the address of what used to be yours, but no longer is. It's an important concept in C. So the pointer is undefined after you've given that memory back. It is said to be a dangling pointer. You as C people, new C people possibly, dangling pointers is really important. You should be able to talk to your grandmother convincingly about why dangling pointers are such bad things. Dangling pointers is a big problem in C, just like memory leaks are. Every good C programmer can talk for hours about memory leaks and dangling pointers. And the last dangling pointer that they had, which caused them a huge amount of frustration because they didn't pick up that it was dangling. And when it dangles, it means it's pointing to nothing. You thought it was pointing to a piece of your memory, but the memory's gone. You've given it back and you forgot. So all it means is a memory address pointing to something that's not yours anymore, for whatever reason. So it's pointing to, sometimes it's said to be pointing to garbage. The pointer can be cleaned, undangled, by just giving it null. That's why a neat programmer, the moment they've finished with their malloc data, will free the data and null it. Gets rid of the dangling pointer. There's no pointer to garbage. Okay, so, and you've given the memory back to the operating system to potentially be reused. The system will free all malloc... going away. When the program terminates, of course, you don't have dangling pointers in any sense because your program's gone. The malloc data, of course, everything you've mallocked is gone. The moment you terminate, it's all freed automatically. You don't leave any legacy. There's no question about that. So you can leave, forget it all, forget about freeing, forget about undangling, sometimes I call it undangling, forget about cleaning the pointer. You can just let the program termination do it. It's not wrong. It's not neat, it's not stylish, it's not elegant, but it's not absolutely wrong. A lot of people do it. Some of my programs, I'm sure, have got unfreed. I don't free the data that I've claimed with a malloc. So if you malloc a lot, though, and you don't free the memory, you will eventually either die because your program exhausts memory, or you will be killed. Because the system will say, you've had enough. I'm going to stop you. And you'll see an example of that very soon. So, Free in the right, yes. This is a somewhat of a sidetrack. Here, just to, well, you may have already seen this already, I'm not sure. I've forgotten in what exercise I've already asked you to do and what I've shown you before, but I thought I'd better include this just in case. You can have a data struct where you have to malloc, and in the data struct you could have a field, variable, that requires another malloc. And in fact, that variable could be another struct which requires another malloc. You could have nested mallocs, in a sense. Be very careful. Don't be too wild with your freeing. If you free things up in the wrong order, then you will actually cause seg faults in your program. So when the deepest gets unmalloced, what gets freed first. So if you have, for example, it's nice to see the code here. Here's a pointer to end pointer receiving something the size of node from a malloc given to malloc. So it has a pointer to an area of memory. If that pointer is okay, then a field in end pointer called at line 6 is then malloced. If that is non-null, I have two pieces of memory. One to store the type, the basic structure, and the other one a field in the structure. Okay, so you see they're quite nested. Looks nested, it is nested. So when you've finished with that internal field malloc, you can free it. When you're finished with the external malloc, if I've got that right, yeah, that's right, the free's right. When I've finished with the external, I can free the end pointer. Have I got that right? Yes, that's right. The malloc happens line 6, and I'm finished with it on line 14, and line 15, I've completely finished the program. Whether it was null or not, I'm now going to clean the pointer, the ultimate pointer, to make sure there's nothing left over and the rest of the program can happen. And if I accidentally will use end pointer, it's got null in there. The system will tell me straight away that there's a problem. At least you won't go into some weird part of memory, overwrite something that you didn't expect, and not be able to understand at all what the hell's going on. Of course, it's sort of working, but it's doing weird things. These weird things usually mean you've got a pointer that's not pointing to what you think it's pointing to. That's what pointers and pointer arithmetic, they can be the tools of the devil. They can really get you into a lot of strife when you're not very careful and very disciplined and are very aware of what you're pointing to, really in control. You've got to be really in control of the program. You can't do them hit and miss. Try something and see if it works. It doesn't work with pointers. Yes? There we go. I was thinking about that too. And would you need to nullify that? No, I can't imagine. Well, you could. I mean, I could have put. I thought about that as well. Should I have here a clean of end pointer to field? Is that what you're asking?
No, I'm asking that we have a malloc for end pointer and we have a malloc for the field.
Yeah. You're wanting to know, should I have a clean of end pointer field? A clean?
If I clean the end pointer field,
Yes.
will the compiler automatically free end pointer field?
That clean can only happen giving it. Well, if you give it null before you free it, and it depends on what you want to do. If you overwrite end pointer anything, end pointer or end pointer field, if you overwrite that data, that address, that pointer, you've lost it. Okay? You really do have lost it. That's the next example, by the way. So the question I see still that's sort of hanging a little bit is when you have nested mallocs, you've malloced a data structure. You've malloced a nested data structure. You've freed the nested data structure because you're finished with it. You've put all the data in that you want. You've initialized it. is there any value then, if you know that you're going to free the total data structure, to first clean the nested data structure? That's still, to me, a little bit of a almost stylistic thing. Because you're cleaning in line 16 the total data structure, after line 16, the field is irrelevant. I mean, you can't get to the field. You can't use it. So, to me, it seems like an academic or technical point of whether you've ever cleaned the field. You free the field, you've got to free the field. If you don't free the field, if you don't have line 12, you're a bad boy. That is criminal. That is an absolute mistake. That will get you penalties. Okay? That will get you bad behaviour. That is a memory leak. If you don't free a malloc, that is a classic case of memory leakage. It is the one thing, it's a bit like the thing that Superman is scared of. C people are scared of memory leaks. The more pointers you use, the greater the chance. The more pointers, the more mallocs you use. They tend to work together. When you use a lot of pointers, no arrays, you tend to be using a lot of mallocs. And if you forget to free a malloc, you'll have memory leakage. And memory leakages have a tendency to build, because every time you've leaked memory, and I'll show you in a moment exactly what that means, we're going to leak an elephant tonight. A whole elephant we're going to miss. I'll show you a little program that does that. So when you leak some information, leak some data, leak a piece of memory, you'll never get it back. Impossible. And if that accumulates, if your program runs not for 5 seconds, not for 5 minutes, not for 5 hours, but for 5 weeks, these memory leakages, they accumulate. And every one is irreversible. And eventually your program dies. The system gets sluggisher, more and more sluggish. The program memory map gets bigger and bigger, and then eventually the system kills it, or it dies itself with exhausted memory. Most C programs running, serious C programs that run for long periods of time, suffer from memory leaks. It is the unsolved problem of C programmers, and the thing that C programmers hate and fear the most. They've got memory leaks in their program. So they spend a lot of time examining, studying, turn it upside down, looking at it sideways. Have I freed all my memory? Because if I haven't, and I run this for a week, and how do you find where it's leaking memory? It's extremely difficult. There are a lot of tools on the market, a lot of expensive tools that do nothing else but try to find memory leaks. These things can really accumulate. Yes? Should it be? Oh, yes, name is wrong. It should be, yes, I changed it to field. Terribly sorry, yes. I originally had name, and I thought, why am I calling it name? Because it was meant to be a name, somebody's name, which could be any length, so I need to do a malloc for it. But then I thought, why am I calling it name? Call it, yes, very good, thank you. That's a mistake I didn't pick up. Okay, does the system really recycle freed memory? Okay, I've said, we've got to free the memory so we don't have a memory leak. Okay, you can sort of believe that, but you've got to see yet what that means, really. But the whole point of this is you get memory with a malloc and you give it back. So the system can recycle it somewhere in your program. If you don't do a malloc later on, you can maybe get a piece of that back, or more back, or half of it back, or whatever you're mallocing. And the system can give it to you again. And then you have this nice transaction with the system. That's runtime. That's what mallocing does. And freeing it, memory goes backwards and forwards. So, here's a little program which I call free check. Look very carefully, see how simple it is. I have just one pointer. In and for loop, one pointer. What am I doing? Oh, I was thinking, I couldn't see. I've been, initially, I'm forgetting, I'm typing it in the for loop. I've tried to stick to that now. Int I equal to 0, to some number, which I'm calling now the malloc number, mal number. I'm mallocing and I'm freeing. And then I'm mallocing, freeing, mallocing, freeing, mallocing, freeing, mallocing, freeing, mallocing, freeing. 10 times. At the end, I'm being really a good boy, and I'm cleaning my pointer, P. Every malloc has been freed. I'm not worrying about checking for the null at this point. I'm freeing it straight away. Whatever it comes back, I'm freeing it straight away. I actually haven't thought about what happens if you free null. It probably should be checked. You know what? I might check that. I might set P to null and see what happens when I free it. The chances are it will seg fault. Never thought about that, never tried it. Because you don't actually ever have a full system very often, so you don't often have a null pointer from a malloc. So freeing a null pointer, I've never had it personally. But it occurs to me in this little test program, I should check for that, because if that seg faults with full memory, then my program has got a bug in it. It's not robust. But okay, can you all see what this program is trying to do? It's trying to see, well, okay. It's got a print statement there, and that print statement prints out the P that's returned by the malloc. So every time I go through the loop, I'm asking for the same amount of memory. So what am I trying to do? What am I looking for here? Someone? Yes. Is it the same P? If it's a different P, then it's not recycling. If it's the same P, it is recycling. Okay, it's obvious, isn't it? It's a very simple little loop. So everything is in the P. What value does it have? And whatever it is, it'll be 10 times the same or different things, 10 lines. So first I did it with DCC. What do you see? Interpret, someone? What's it doing? Are the numbers the same? The address is the same. Are they the same, the numbers? They're not. So what's that telling you? It's increasing. But why, if I've freed it, I'm being a good boy, I've freed it. You see it, free P. I've given it back. The computer, the system has that memory back. Why can't I get it back again when I next do a malloc? Because I've given it back. It's not recycling. It's ignoring the free. In fact, I didn't even try that. If I took the free out, I think there's a 99% chance, I mean, I've given myself a little exercise now, maybe you'd like to do that. Just take the free out and see if it changes. You can do that on your home computer. Because if it doesn't change, well, the free's not doing anything. It's all a big lie. Well, maybe you should do it, but the system is ignoring the free. It's just finding another piece of memory. The first time it gives you something from 30, then it's going to 50. Now, why it's 30 and 50, who knows? I haven't got control of the compiler. I don't know what instructions it's generating. Because when you look at the program, the mal size, the amount I'm asking for, is 16 bytes. Deliberately. 16 bytes. That address there is a hex address, which is base 16. So I would expect the first address to be 10, the next one to be, if it's not going to free and give me back what I've just given back, I would have expected 10, 20, 30, 40, 50. Instead of giving me 10, 20, 30, 40, 50, etc., it's giving me 30, 50, 70. So it's padding for some reason we don't understand, that I don't understand. I can't see why it would do that kind of increment. But in any case, it is consistent, and the point is it is not recycling. That's evidence. Out of curiosity, I tried GCC. GCSE free check. What do you see now? What does that tell you? GCSE is recycling. GCSE, G means green. I just thought of that. I just did think of it right now. Nobody, I'm sure, has ever thought of that. Just on our system, GCSE, this version of GCSE on our system is a compiler that's green. So if I ask you that question, is GCSE green? What do I mean by that? In the quiz or in the final exam, will you know what to say? Will you know where I'm coming from? And anybody who has not been in this class wouldn't have a clue what that means. Green GCSE, what the hell are they on about? But it's recycling. It means that when you free, you get back what you gave it back. So every time you do a new malloc, you'll get back what you just had. It's being really space conscious. I was so impressed when I saw that. I've always had a soft spot for GCSE. GCSE always gives me a bit of bit nervous. It's just too finicky, too long explanation. Most of the time I don't like reading it because it's all over the place, and I think, well, just tell me what's wrong. I don't want a big story about what I should be doing and how I should have had a better childhood or something like that, that sort of thing. It's telling me too much. I just want to know what's wrong in one line. GCSE is more succinct as far as that's concerned. Okay, so I've run GCSE and DCSE for our free check, and I've now seen who recycles and who doesn't, and I did not expect them to be different like that. Okay, memory leaks. Memory needs careful management. This is a responsibility. I've said that the thing the C programmers fear most in life are leaks. Serious C programs write very complex programs with very complex pointer handling, arithmetic, and it's very easy to have data, memory allocated that you don't free up and it accumulates. So the first rule is don't lose your memory. For most of you that's not a problem. For people of my age it starts to become really interesting and it becomes a problem. Don't lose your memory. It sounds like a thing of life. But in C, it's really very powerful and very important. It's a real important, it's a quality measure. If you can prove, it's impossible, but if you can show your program has no memory leaks, you're very good. You're a fantastic programmer. But it's extremely hard to prove that. You really have to show that every piece of logic in your code, whenever you've done a malloc, that there's a free somewhere down the path. Everywhere. In every possible if statement, loop, whatever. And that can be extremely difficult to demonstrate. So, okay, first rule is don't lose your memory. If you overwrite a pointer from a malloc, you've lost memory. The memory is still allocated, but you can't get it back. You've overwritten it. You can't even free it, because to free the memory that you've lost, you need to have it. You can't free something you haven't got. It's cruel, but it's the way it is. You have to have it to free it. So you can't free it, you can't get at it, you can't see it, you just know it's gone. Goodbye. Okay, here's a little program which is as bad a piece of programming that I've ever seen. 4 nasty lines of code. 4 lazy lines of code. Just think about them for a moment. There's a little function there that takes an argument, which is just a simple number, and it returns a malloc. Ooh, straight away you should think, I'm a bit nervous about that. Looks a bit funny. But malloc just returns a pointer, doesn't it? And that returns a pointer. So it sort of makes sense. It looks like it might be type correct. Now I'm calling it, that could be main if you like, and I'm get memory 20. What's wrong with that program? Why is it so bad? I don't know what you mean, but I'm going to put you down for a moment. You're on silent mode. some... Yes, it's not assigned to anything. Get mem, but 20, okay, it's come back with something. It's throwing it away. It's not doing anything with it. It's not assigning it to anything. It's throwing it away. So what's it done? It's lost the pointer to 20 bytes. 20 bytes of memory, whoop, out the window. Gone. We'll never get it back. Disappeared. That is an inbuilt, that is actually committing suicide, your program. You've actually destroyed your own program. There is no way you can resurrect that program. Well, you put an assignment statement in it. But if you're that lazy, well, the problem started with the malloc. You're not even checking for it on null. So you're as lazy as can be. Return malloc. What idiot would do that? You've got to check what you get back and guard it with your life. Because that pointer to that piece of memory is all you've got. If you throw that away, you've lost that memory. Okay, so there's a 20-byte leak. Here's a program that leaks an elephant. I'm reserving on line 8 num bytes, 10 bytes of memory. Nice little malloc. If the reserve is null, okay, I've got a problem, but assume that's not the case, so it's just the usual test. I now start populating my memory directly, straight into the memory. I'm putting my E, my L, my E, my F, my P, my H, my A, my N, my T. And how am I doing it? I'm using pointer arithmetic, and I'm changing the value returned, the pointer, the address returned by the malloc. I'm actually changing the malloc. See that reserve plus plus? That's going to change the value of that reserve by 1. Changing this pointer is living dangerously. You need to protect your pointer. I'm moving on. So where I started, I'm going to lose track. Now the person that wrote this is very arrogant. Of course, what he says is, I know what I'm doing. There's no problem. I can tell you what's there because I just have to take off 9 and I'm going back to the start. I know I've done 9 characters. Now, of course, if you change an elephant to a zebra, you've got to make sure you get your 9 back right. So this is a magic number, 9. You've got to be careful. It depends on how many assignments you've got, how many increments you've got, whether that 9 works. Of course, it's just pointer arithmetic, 9 to the right. I finished the T. Oh, where did I start? Oh, it was 9 back there. I haven't forgotten that. Thank goodness. But now I do that line, reserve equals malloc of some number, num say. Now I'm gone. Dead. Elephant is somewhere in memory. I have no idea where. Think about that. You have an elephant in your computer memory and you don't know where it is. You can't see it. You can't free it. That reserve with that elephant is invisible to you. Okay? It's disappeared. Of course, you've lost the starting address. I was smart by doing that printf to say, I put in elephant, it'll print out elephant, then I've moved on. I didn't free. I could have done there, if I was really, I suppose, being correct, I could have put in there, printf free reserve -9. To be honest, I've never done something like that. It almost seems to be, it's weird. It's a weird program to think that way. Because what you normally do, of course, just like I did in Dynamica, I had a pointer that, remember, that started with Dynamica, D, and I incremented D. I didn't touch Dynamica because that's the starting address I don't want to lose. I shouldn't touch that reserve at the start there. And I should have had another variable that actually did the increment to get the letters into the memory. That's the right way of doing it. But I was being lazy when I wrote that program, and I tried to do it without save one pointer. I'll use the returned variable from that malloc call. So there's a 10-byte memory leak. This is poorly written. That is also leaky. The first address is reserve is lost. When the second malloc is done, there is no way of getting that back. You've lost that reserve and its element of course. When a program terminates, all the memory the program uses is automatically freed. The system will do that obviously for you. It is not dangerous to forget to free memory at the end of a program, but it is poor style. It is dangerous to not free memory within the program when you don't need it anymore. Every time you keep your memory open, a malloc unfreed, that is a potential 1, leak, and 2, corruption. That the data could be corrupted if some pointer gets a value to that space and changes something just because you lost track of what you were pointing to, which is so easy to do. We can go a step further. Not that much more to go. We know malloc will return null when memory is exhausted. We know that that malloc returns null. Now, I would imagine 50%, maybe less, of you would immediately think, can I write a program which would keep mallocing until it's null and tell me how much it's malloc and tell me how much memory there is? Indeed, can I crash the computer by mallocing and mallocing and mallocing until it's null? So when it's finally hit null, will it crash? Can I break it? There must be a number of you who would say, can I break it by using the fact that I can keep on going until it's null? A stress test, if you like, or a piece of hostile hacking, if you want to put it that way. So here's a little program that does just that. You see the main program here at the bottom? Just calls exhaust, and it says how many blocks it's found. And exhaust, it has a struct block of 1024 characters. 1024 is usually the block size, but it could be anything really. I have a counter, I do a malloc, and while that block is not null, the return from the malloc, I'm incrementing my counter. I want to count the number of blocks I'm reading, and I'm getting another block. I'm printing the count and the address of that block. So I'm going through memory, counting how many blocks I can read. I'm freeing nothing. I'm overloading memory. I'm stressing the system. I'm going to see if I can grab all of memory and crash it. Okay, this is a nice piece of hacking. Everybody see what it's doing? No freeing going on deliberately. I don't want to free a thing. Although with DCC, it appears it doesn't matter because it just doesn't recycle anyhow. The freeing doesn't seem to do anything. Who knows? Here, I'm deliberately not freeing. Do not free block, because I want to grab another block and another block and another block and another block and another block. How far does it go? What does it do? And of course, we've got DCC and GCC as well. The program does not finish or exhaust memory. The program does not finish or exhaust memory. If it does not finish or exhaust memory, it is killed by the system. So what actually happens? When I use DCC, this is the output. You see the first block address it's given me is 580. The next block it's given me is A80. And then the next one is G or E80 or something like that. It's 4, 6, 5 more, 4, 5 more. Then 580 plus 5 is A, plus 5 on A is F, D. F, that's A, B, C, D, E, F. Yeah, so it would be F80, and then plus 5. And it just goes on and 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 on. And eventually, after 1,481,000 blocks, it comes up with killed. The system's killed it. Doesn't let it go on anymore. I've ran it many times, different circumstances, but it always comes up with 1 or 2, sometimes a 346, sometimes 342. It always stops about there. That's having compiled it with DCC. So what I've done there is 1.5 million blocks I've claimed. I've freed nothing. I've been a really naughty boy. But, okay, I can see what the memory available is. So that would be the exhaustion, maybe. Yeah, of course, it stopped. No, it hasn't. What am I saying? There's no null. No null here. It's never picked up the null. The system has killed it. I ran this program a couple of years ago on the 32-bit machine that we used to have here, before we went 64. And then it did come up with null, like clockwork. Took it only a couple of minutes, came up with null, no more memory, and reported, and from memory it was about 300,000 blocks it would give me. And then memory was full. So it had quite different performance. I was expecting the same kind of thing this time. I still had the output from last time, but this time the system has interrupted the program and has killed it. Using GCC, same thing. GCC, the program is killed, it just happens later. Sort of verifies, to me a little bit, GCC in some sense, it's a bit risky saying this, but it's a bit more serious. With GCC you get a bit more memory. You get here 2 million blocks. That's a bit, 25% more than DCC. Okay, so again, I say 2 million blocks I've been able to get from malloching. A block is 1,024. I could have made it blocks of 10,240 as well, of course. It makes no difference. It's just how much I want in one hit, and I want to do it incrementally to see what happens, whether the system crashes, what it does. And in both instances, the system will stop you. Now, in a sense, thinking about it, it's not unreasonable, because the difference between a 32-bit machine and a 64-bit machine in terms of addressing is enormous, absolutely enormous, astronomical. If you were trying to exhaust memory in a 64-bit machine, that is something that really could take a very long time. So they've protected themselves with 64-bit technology with the compilers and said, look, there's a point at which we stop. I don't know if it's time, some kind of internal clock that stops you after a while, number of mallocs, size of mallocs, I don't know. There's something in the compiler. When it generates the code, it's got to check on it that if you are too greedy, it'll kill you. Okay, unlike the 32-bit machine, where it was happy to exhaust memory. Or happy to. I'm sure the system administrators weren't happy when you were doing that, but it worked fine. It literally did exhaust memory. Okay, the last topic is realloc. If space returned by malloc is too small and you change your mind, think about that. I've malloc, but I regret how much I asked for. I want to change it. Can you? Well, yes, you can. Amazing what you can do with C. There are things in the corners and hidden that some people have never heard of, that know about. You look. So here I've got a pointer that's returned by a malloc, size in bytes, and I've got I've done it again, I think. I've changed the name of something. Yes, I have. I think I've got an inconsistency. I've got a new pointer, PEXT, P extended, or extra, P extra. P extra has got an extra argument. Look at that extra argument. What is that extra argument? What is it? P. Where does P come from? Malloc. It takes Me's P's, it takes the malloc. The first malloc's pointer. It uses it. It knows what it is. If you put any other pointer in there, the system will, oh, what are you doing? Fault, error. But you put a malloc in there, a malloc pointer, a pointer returned by malloc, it will extend it for you. That's food for thought. It will extend the amount of memory it's given to you. And you could do this again, and again, and again. Every time you decide you want more. Give me more. Give me more. Give me more. Keep on going. It's fine. You program that in to give me more. You have to, of course, know when to ask for more. So how does it work? Because that's a very simple little program, and there obviously is going to be some care that's needed here, because what happens to P? What do I free? Can I dangle? Can I leak? What's going on? How much danger am I in? Is this a minefield? Can it blow up in my face? What can happen to me here? Now that I've got two pointers that are closely related, they're linked. And one is bigger than the other, or points to a bigger area of memory, and what's happened to the old one? Is it subsumed, or is it in there? Or is it another piece of memory? And do I need to free? I mean, all these questions should immediately come to you. What have I got? How much danger am I in? This is what the question should be coming to you, just one after the other. You should be able to write a list of 30 questions, asking you each one. What is the question you have? Now consider the following little program. I call it Mandy. What does REAL stand for? Yes, Realic. Tricky, isn't it? Realic, real, first four letters. Mandy Realic. Malloc, too few bytes to store the string space, so do a Realic. So my program does a malloc with too few. 4 bytes. Space is 5 bytes. Oh, dumb. Made a mistake. So I've got my malloc. I've checked that it's null or not, and I've assigning, just like the elephant, to that P. Notice the care of which I'm doing it this time. Why am I doing that? You're on silent mode. Why am I doing it that way? What's going on? I'm putting SPAC into memory. That's pointer arithmetic. I've seen a few of them now. Getting used to it, I hope. And what's it achieving?
Array type arrays.
Behavior like
Arrays.
don't understand the word.
Arrays.
Arrays, an array. Behavior like, I hate that word. I want to, not only the assignment, it should be forbidden in the course. We should have an array-free course. Just imagine, would that sell, I wonder? Would students come? My goodness, the ultimate, an array-free course. Wouldn't that be? It would be possible to give this course and never to use that 5-letter word, array. It would be possible to do that. It would be a bit strange. And I'm sure students would use it, but you could have this simple. Every time you use that word, you have to put $2 into something. And I see how much money I get at the end of the session. It's like swearing. No arrays here. We don't want to think about that. We're serious C people. We've got pointers. Now, here, I've got my P. I'm adding 1 to it, and I'm putting in the next letter. Then I'm adding 2 to it. Why am I doing it 1, 2, and 3 and all this? What's the point? Obvious. I don't want to change P. Remember the whole thing. I don't want to lose my P. My P is the return address from the malloc. I'm not allowed to lose that. I've got a leak. The theme tonight is leak-free. No leaks. I've got to keep the starting address, that pointer, that value from that malloc, right through my program, and free it at the end. Then I can sleep nights. If I don't do that, I'm a bad person, I'm sloppy, I don't deserve to be in this course in any case. You must free the location that you started with, which means you don't change it. If you change it, you're in strife. We saw that with the elephant. You change it, you put another malloc on top of it, you're gone. I started incrementing the pointer, reserve, with the elephant. I was already playing dangerously, doing that. Here, I don't want to touch my P. It's still a bit iffy code. I'm using pointer arithmetic, but at least I'm not changing my P here. But I'm not far from it. So, okay, I'm putting the SPAC, the first four letters in, and when I put that E in, knowing that it's just 4 bytes, what happens? Oh, I like it, but just like a lot of students, you complicate things. But you're right, but it is still one notch too high. What's the problem here, basically, more simply? Not so much technical stuff. What's the problem? So, what actually comes back with, it's exactly right, there's no technical things in there really, well, I suppose it's technical, but probably what happens is you get a buffer overflow. Why it calls it a buffer, I don't know. Memory buffer overflow is the error message you will get. And you'll scratch your head and think, I thought I did that all right. You've got to remember, sometimes you have 500 lines of code here, and it gives you memory buffer overflow. Oh my God, where's that now? What's the problem here? And you've written a byte too much to something, maybe a hash def or not. Maybe you've got some other variable expression to tell you how much you want to allocate. And you haven't allocated enough, you've miscalculated. So that star P plus 4, that will certainly go wrong because that's the 5th byte and it's only you've asked for 4. So it will do. That's what I said before, malloc is serious. You're not playing games. Malloc will protect its own memory and will only give you what you ask for, and you go outside of that, just like an array, I shouldn't have said that, just like that thing, it will come back with an error. It'll hurt you. Now, more so, if you try to put another one in, yes, that's interesting. The next one, forget that line, P plus 4. If I do a printf of P, I want to print the SPAC. I'll put that in memory. I've got its address, P. I want to print it. I'm not overwriting anything. Now you come with your answer. Your excellent answer. There's no null. SPAC, where's the null? System just says, I'm looking for a null and memory buffer overflow. So either the P plus 4 line, line 20, or 21 will give you the same error. Because both of them look for number 5 character. And in any case, well, the percent S is looking for a string null terminator. It doesn't find a null termination, doesn't know where to stop, realises it's got the end of memory, the malloc, and it just says, look, I've got no end, I don't know what to do. I'm overflowing here. Okay, so as C programmers, you now sort of, okay, I know what's coming to me, I know I'm getting an address here, and I know why that would go wrong. You can anticipate that. But okay, let's back to where are we going here? We're saying we want more room. We've changed our mind. We realise now we've made a mistake and we want to do a realloc. Now, a realloc is a bit of a weird beast, I warn you. And this is the realloc here. I've now told it I want 6. Now, these are, I have to apologise,